There we go. All right, so Hess's law. If we're looking at Hess's law, we got a series of steps, and we say this particular reaction, if we start with C4, which is methane gas, burn it up with some O2, combustion reaction, that the overall reaction, if we look at everything, is an exothermic reaction, and that makes sense, right? Combustion is going to be releasing heat energy into the universe as it happens, so that makes sense that the reactants are at a higher energy level than the products are. But this is not actually how the reaction takes place. The reaction actually takes place in a series of steps. Initially, you'll take the CH4 and this O2, and you change it into CO and H2O, and I don't like this half of an O2 because in reality you really can't have a half of an O2, but they're just showing you how it's balanced. So this is the first step. The second step is where you take these are the reactants, and the final product then is the CO2. So we say that the series of steps, the H2, the enthalpy of H2, and the enthalpy of H3 should sum up to be what enthalpy? The enthalpy of what? H1. Do you see how that works? So if we looked at the overall enthalpy change of the whole reaction, which we call H1, is a negative 890. If I add up the enthalpy of H2, which is half of the step, and the enthalpy of H3 was just the other half of the step, when I add up the negative 607 and the negative 283 together, what number should I get? The negative what? 890. All right, so that's what Hess's law is saying, that you have a series of reactions that take place in steps, that the sum of the steps has to equal the overall change in enthalpy. So these things started out with a higher energy. They were containing energy. They went down to a state of lower energy, and that's why we say Q left, right? Q left the situation because the reactants were higher energy, the products were lower energy, so some Q had to go out into the universe. So the initial versus the final. So the enthalpy of formation is that table that I gave you Tuesday in class. Remember? The delta H sub F values. Remember, there's three different choices when we're talking about the enthalpy of formation in terms of their signs. When we look at that table of enthalpy of formation, what were the three different signs that we encountered? It was positive, negative, or zero. What were the things that were commonly zero enthalpies for the universe to create? What were the things that we always saw that were usually zero in that table of enthalpies of formation? Most metals, not just all solid, but you're talking about a metal solid. That's because at the Big Bang, right, all this stuff happened. All these particles were shot out from the Big Bang into the universe. And metals were part of that Big Bang. They just existed at time equals zero. What else had enthalpies of zero besides metals in their solid state? A lot of diatomics had enthalpies of zero. All right, if an enthalpy of formation is positive, what does that mean about, did the universe have to put energy in to make that thing, or did the universe get energy out? And when it made that thing, if the enthalpy is positive, you had to put energy in. So it cost the universe some energy to make that thing form. And then conversely, if the sign of the enthalpy of formation is negative, what does that mean about when that thing was formed? The universe got some energy back as a result, all right? So that's what when you see that value, the delta H sub F, that's the individual enthalpy of formation for that thing, not a whole reaction, just one component, all right? And that's why it's on those tables as a component. And there's a sample of the enthalpy of formation. And if you look, and they standardize it, they say at 25 degrees Celsius, because the enthalpy of formation is going to change if the temperature changes, because the state of matter that they would exist in would also change, right? So we have to standardize it some way. We say it's 25 degrees Celsius and standard air pressure at sea level, which is 1 atm. Now we're going to talk about enthalpy of reaction and how you use Hess's law, right? Hess's law says that if you have the individual enthalpies of the formation of the reactants and products, what's the overall way that we calculate the enthalpy of formation? What's the formula to calculate the enthalpy of formation? The sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. Okay. All right, so that's what you're going to use when you're calculating the overall enthalpy of the reaction. So they may ask you, on a homework problem or a quiz or the exam, calculate the enthalpy of the reaction or the heat of reaction. So they're talking about the overall amount of energy that's either expended or absorbed as a result of having that particular reaction occur. All right, so if we're looking at the calculation of this idea of enthalpy of the reaction, if we take a reaction that happens in a series of steps, like this first reaction here that happens in a series of steps. I'm going to split the screen here if I can, and why is that not connected here? Let me check this really quick. That's the one I want. Why is that one not? Get a little pause here. If I can use dual screens, we're going to be in good shape. Dang it! Why is that not working? All right, let's try this one. They're both fuzzy. What the heck? Well, it looks good in here. I don't know why it's not showing on there. I'll try to unplug this one time. See what that does. Sometimes that prompts it to do what it needs to do. Okay, well, let's try this. Can I split the screen is my next question. Kinda, sorta. All right, let's see what I can do this way. All right, I think I can work with this. All right, so if we're looking at what I've got in that reaction over there, if you look at the unfortunately we can't see. Let me scooch this over just a smidge. Okay, I want to see over here. See the energy diagram? This is the enthalpy, so this is low enthalpy, this is high enthalpy. You could also consider that energy. So we're looking at this first part of the reaction. The overall reaction is the C3H8 gas. So we're going to write that down initially as the C3H8 as a gas, plus the other part of the reactant is the 5O2 gas. 5O2 gas. Now, in this particular reaction, I'm going from an energy state that is lower to an energy state that is higher. So my products in this particular reaction go from that to this 3C. I'm just going to abbreviate it GRAP, right, the graphite, plus the 4H2. You should be writing this down as a gas, plus the 5O2. Also as a gas. Now, if I look at the enthalpy of formation there, unfortunately I'm running out of paper, so I'm going to put the enthalpy of formation for this stuff up here as a, what is the enthalpy of formation there? We're looking at just the area of this energy diagram that's highlighted with the pink bubble. What's the enthalpy of formation there? 103.85 kilojoules. All right, so I'm going to put that up here, which is a plus 103.85. So I had to put some energy into this. So were the reactants or the products at a lower energy level because I had to put energy in? What were at a lower level? The reactants or products? Reactants were at a lower energy level. If you look at the energy diagram here, the reactants are at a lower energy level, the products are at a higher energy level, so you must have had to put some Q in, right? Q had to go in to bring those reactants up to a higher energy level. So it cost you energy to take that C3H8 and use the 5O2 to decompose the C3H8. This is not a combustion reaction, right? This is decomposition. You're taking the C3H8 and you're breaking it up into 3 Cs, 4 H2s, and 5 O2. So that's the first part of the reaction. All right, now if we move this cursor, let's see here. This may be. All right, so now I'm looking at the second one. And I'm looking at the second reaction. In the second reaction, I take the things that were my reactants initially, my 3C, as graphite, should be writing this down, plus the 4H2, leave some space in between each of the equations, plus the 5O2 as a gas is going to produce, now what are my products for this reaction? If I'm starting with my reactants up here, what does it give me as products for this step of the reaction? What are the products here? Can you see that? 3CO2, all right, 3CO2 is a gas, plus the 4H2 gases, plus the 2O2 gas. I'm going to put the enthalpy of formation in here because I don't have room on my paper, which in this case is a negative 1181 kilojoules. So now, my reactants started out at a higher energy level, right? My reactants had more energy than the products. So was this an exothermic or an endothermic reaction? Exothermic, and we know that because the sign of my delta H is negative, right? Heat is leaving, so Q had to leave. If the reactant started out at a higher energy product, higher energy value than the products were, so Q had to leave the whole situation. All right. We go on to the third step of the reaction. Now it's highlighted a little bit differently in the pink. We can do the same thing. We take the products that we had over here, the 3CO2, which is now as a gas, plus the 4 H2s that we have as a gas, plus the 2 O2s that we have as a gas. And now, what are my products here? 3 CO2s as a gas, plus the 4 H2O liquid. Yes, question? I don't think so. I don't think so. I just had to kind of do the best that you can in here. So we got 1143, so it's a negative 1143 kilojoules per hour. All right, now I go to the last step of the reaction. Right, I'm going to go, okay, now we're highlighting this last part. This is what we call the overall enthalpy. So really the reaction, this is what happened. It started out, these as the reactants, we write those as the products. So that's what we call our target equation. Whoops. So in the target equation, what you're going to do is you're going to put a line. You're going to have the target equation. And the target equation you have is the 3 CO2s as a gas plus 4 H2Os as a liquid, which gives us our final products here in this case. Did I make that wrong? I did. Whoopsie. My overall equation is the one that's at the bottom of the slide here. Let me get this out of the way. Right there. So we're going to write the C3H8 plus 5O2. So you should write that at the bottom. C3H8 as a gas plus the 5O2s, and I'll show you what I'm doing in just a minute, gives me 3 CO2s as a gas plus the 4 H2Os as a liquid. All right, so what that's going to look like is this. Now, I'm going to move this over because we're going to use the equation a lot more. All right. What they want us now is to calculate what's the overall enthalpy of the whole reaction. This is a different way of calculating and using Hess's law. Now what I have to do is similar to an operation that you've done in algebra when you solve by adding equations together, right? Solution by addition. You've done that in algebra before. Similar thing. What you're going to look for is you're going to pretend like these arrows are equal signs. And you're going to look for opportunities to cancel common quantities on both the reactant and the product side of each of these equations so that I end up with this is my overall equation. So let's look on both sides. Let's see, what do I have here? I got some H2s on both sides, right? I got H2s. If these are all equal signs, I got H2s on both sides. I can cancel those. So I'm going to cancel those two H2s. Let's look for other opportunities. What other opportunities do you guys see that I could cancel stuff on both sides? 3 C's. We got a 3C here and a 3C here. Absolutely. We can cancel those.
Do we cancel all the 4X's?
There's 4 on each side. We got 4x here and 4x there. Well, we're only just going to cancel each on both sides, right? Because we got 4x and 4x. I can't cancel 4x and 6x, right? Just hang on. So 3 C's and 3 C's. What else can we cancel across the board? That's easy peasy to look at and cancel. CO2. I got 3 CO2s there and there. Here's I've got 3 over here. So I'm going to use that one and that one to cancel. Anything else? I got some O2s. I got 5 O2 here. Where else is my 5 O2? Oh, there it is. I didn't see it. It's hiding out on me. All right, there's a 502 and a 502. We cancel those. Is that it? I think we're good. And now what we're going to show is that that equation comes down here. That part of the equation, right? And I'm solving by addition here. I have this one that remains, which comes down there.
Can you cancel the 202s?
Let's see. Did I not figure something out? Oh, yeah, I forgot to cancel these, didn't I? There we go. What else? And 202s? Yep, there you go. All right. So we still got these that came down, so we're good there. What else is falling down here? We got the CO2s and the H2O. All right, how do I calculate my overall enthalpy of the reaction? You sum up all these, right? So we take a plus 103.85, a negative 1181, and a negative 1143. I'm doing the add and subtraction wrong. I didn't pay attention to my signs. Somebody with a calculator, give me the number here. It's going to be a negative number. All right. Let's do it the same way we did it on Tuesday. Using the overall enthalpy of the reaction, according to Hess's law, is the sum of the individual enthalpies of the products minus the sum of the individual enthalpies of the reactants. I can figure out the individual enthalpies. You got that table. Get that table out. What's the enthalpy of, let's see, it's propane gas, C3H8. What's the enthalpy of formation for C3H8?
Negative 103.85.
Thank you. Kilojoules per mole. Well, I bet this is 0. How do I know that? It's diatomic gas, and it's in its gaseous form, so I know the enthalpy of that is 0. What's the enthalpy for my CO2? Formation of enthalpy. On your chart that I gave you, your table of enthalpies. Okay. Kilojoules per mole. And finally, what's my H2O's enthalpy of formation? Negative 285.84. Thank you. Kilojoules per mole. All right, these are my enthalpy of formation values, and we get those from Appendix C in your textbook. Now let's use Hess's law and make sure that we've done our work correctly. So now I want to sum the enthalpy of the product. So the delta H of the reaction is going to be the sum of the product's enthalpies, all right? So now, each one of those, to make one is negative 393, but I got 3 moles of that I'm making, right? So I got to take 3 times the enthalpy of the carbon dioxide, which is a negative 393.5. I'm not going to put the units in there just because we're saving time. Plus, now, each one of those costs me 285.84 K kilojoules of energy would be expended into the universe, right? So, but I got 4 of those, right? Coefficient of 4. So I got 4 times the negative 285.84. Close the bracket. I'm going to put the other stuff, oh, well, it won't be too hard here, because I only have 1 of those, and each one is negative 103.85. I don't have to worry about the O2, right, because its enthalpy of formation is 0. So now, if we look at these values, right, I got a negative, and what happens when I subtract a negative number? I'm actually adding it together. So somebody with a calculator, let's verify, what number should this be? Let's hope so. It's nice if it works out the way it's supposed to. Is it?
It's because you get the decimal. One of the worst things is the decimals off.
Did you get negative 220.15 kilojoules for the overall enthalpy of the reaction?
It's the same number, but it's 0.01.
Okay, well, we're close enough for Gen Chem 1 work, right? Okay, there's 2 ways to solve Hess's law problems. You will have to do this in lab next week. You have an experiment where we're going to give you the overall bottom line. We're going to give you the target equation, the thing that's below the line when you're adding the equations together. That's called the target equation. We're going to give you the target equation in lab next week, and you're going to have to figure out the interim equations and measure the enthalpy of the interim equations, and kind of have to figure out the enthalpy of the whole thing. So you're actually doing this in lab next week. So if you got Monday lab, you'll do it before the test. If you got Tuesday lab, unfortunately, you'll do it probably either before or after the test. Okay, so there's that type of problem. That's a Hess's law problem. Now let's take this top equation. We're going to do one more type of calculation that you're going to have to do for the exam. And I'm just going to use this top equation because it's a handy one to use, and we've got it available. C3H8 as a gas plus the 5 O2s as a gas yield 3 C's as graphite plus 4 H2s as a gas plus 5 O2s as a gas. All right. The enthalpy of this overall reaction, this reaction, is a plus 103.8. And this is 103.85 kilojoules per mole. If I said I've got, I'm just going to pull a number out of the air, 11.5 grams of this propane gas. And I want to decompose all 11.5 grams of that. And I want to know how much energy is it going to cost me, right? Because this is a positive value, I'm going to have to put energy into this in order to decompose this stuff, which makes sense. You're going to break junk up, you're going to decompose it, it's going to cost you energy. Well, if I got 11.5 grams of this, how much energy am I going to have to put in to decompose all 11.5 grams of that? Well, my universal method for chemistry solve problems. I have no idea where to start with. The first thing you should do. Convert 7 moles. Right? We convert to moles. We take the 11.5 grams of the C3H8. All right, that sounds like a good starting point. So we want to go from grams of C3H8 to moles of C3H8. Carbon is 12 each, that's 36 grams due to the carbon, plus 8 more from the hydrogen, 44 grams per mole. Somebody with a calculator, what's 11.5 divided by 44? 0.26 moles of the C3H8. All right, did the conversion between the C3H8. Now, I need to get from moles to energy. Brian.
Didn't you just multiply the whole thing and got 126 moles
Actually, I think you're thinking about that pretty right. So we take the 0.26 moles, and this unit gets me from what to what? What does that unit get me from and to? I've got moles, right? I want energy. The question asked, how much energy would it take? How much energy would I have to put in order to decompose all that 11.5 grams? Well, now I know how many moles it is. And this is my quantification of energy per mole. So all I got to do now is set it up with moles on the bottom, kilojoules on the top. My number is 103.85, but that's kilojoules per mole. Luckily, with the propane gas, my coefficient is 1, so it's assumed to be 1 mole. So now, something with a calculator was 0.26 times 103.85. 20.1, and what are my units here? Kilojoules, just kilojoules, remember, because moles cancels. So that's the amount of energy it would take to decompose 11.5 grams of the propane gas. Let's try a different problem, because now we've got a coefficient of 5 that I want to make sure that you know how to deal with. Say, for example, we had tons and tons of propane gas, but we had only a limited amount of oxygen. Say I have, I've only got 5.1 grams of oxygen, but I want to use all of it up. Okay, I got unlimited amounts of propane, but that's my limiting reagent now. I only have 5.1 grams of oxygen. So what's the first thing I need to do with my oxygen? What should I do with my oxygen first? Convert to moles, right? If all else fails, you have no idea what to do. Find something, convert it to moles. All right, how much does a mole of O2 weigh in grams? 32. Okay, 16 is a common error. Don't make that on the exam. Got to have 32 grams per mole. So what's 5.1 divided by 32? 159, thank you, moles of O2. Now what am I going to do with that moles of O2? I got to use my energy term, right? My energy term, my enthalpy tells me energy to moles connection. So now I'm going to say moles and energy, but now I have to step back and think. That's the correct amount of energy, plus 0.1 or 103.85. But now I got 5 moles of it every time I run this through. So now I have to put the 5 there. That's super duper new and important, and you guys have never done that before. So I want you to pay attention on why that's happening, right? This was a coefficient of 1 for the C3H8, right? This is a coefficient of 5 for the O2. Now, with your calculator, if you have parentheses buttons, here's how you use your parentheses buttons. You take 0.159 times, open parentheses, 103.85 divided by 5, close parentheses, equals, and what do you get? 3.31, and what are my units here? 3.31. What are my units here? Kilojoules. All right, so it cost me a lot less energy. Let me ask you one more question before we jump into the quiz. If I took this original equation and I flipped it, okay, everybody stop writing and pay attention. If I took this equation and flipped it, what would be my value of my delta H? Negative. Very good. What if I took this equation and I multiplied all the coefficients by 2? I make that a 2. This is now a 10. That's a 6. That's an 8. And that's a 10. Now, what would my enthalpy of formation be? Exactly double. Make sense? Okay. Let's try this quiz. Take out a piece of paper. No notes, no tables of enthalpy. You cannot have anything out except your handy-dandy partners in the class.